Okay, welcome to episode 8 of Abundance. Um, in the last episode, I talked about this solar powered hologram burner that that's what I think it was from this 1886 engineering magazine. And I just wanted to uh, go back to the episode 6 where I talked about lighting and carbon arc lamps and Thomas Edison and his incandescent bulb, something I totally missed, or I kind of skipped over it because I wasn't, I was focused on other stuff. But this was this is the discussion about Edison. This one section in this Cassier's magazine about the life and inventions of Edison. I kind of talked about this in episode 6, but let me just show you here. So he sent a bunch of these. A bunch of these experienced agents to the Amazon, his experienced agents that he called them, to the Amazon to look for fiber to use in his incandescent bulb, even though he was like working with platinum and all kinds of other metals. So why did they go down there? And then this was the section in this article was an unpublished account of an expedition to the Amazon in conjunction with that guy, that guy, that guy, a member of Mr. Edison's mining force. Okay, miners, and himself, blah blah. It exemplifies in a very striking manner the whole souled way in which Mr. Edison's associates lend themselves to the furtherance of his views. Okay, and then when they were in the Amazon, his experienced agents there, they wanted to go up to one section of up the river, and the Indians were like, nah, 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 nah. And so, listen to this. The society of these gentlemen was attended by some inconvenience, for although harmless in other respects, they were inveterate thieves, and a strict watch had to be maintained day and night upon the jewelry and other valuables deposited at the bottom of the boat. So his agents went down there, his miner friends, like mining for metals, went down there to steal jewelry and other valuables. And the Indians were like trying to probably take it back. And they're like, oh no, that's ours now. Like probably some stupid thing like, oh, you gave it to us, right? Something like freaking Duper's Delight. All these guys are. So what I'm getting at is more kind of more evidence that they were trying to obtain old jewelry and valuables because they could have had smoking gun evidence of our lost history. Okay, so let me now let's talk about oxyhydrogen. So this is from 1911, talking about the oxyhydrogen flame. But today we have like oxyacetylene welding, which I believe is like super common and one of the main ones. Anyway, I'm not a welder. But hydrogen gas, it burns straight with air, the oxygen in the air, or you can give it straight oxygen and hydrogen in the right proportion, and that will get you the hottest flame. And all what does it result in? Water, water vapor, steam. So it's literally the cleanest burning fuel. Is there anything else that burns, produces heat, and then the result is water vapor? Anything? No, this is the cleanest, best stuff. That's why we should be using it. Um, many, many forms of oxyhydrogen lamps have been invented, but the explosive nature of the gaseous mixture rendered them all more or less dangerous. It acquired considerable application in platinum works, this metal being only fusible in the oxyhydrogen flame and the electric furnace, and also for the production of limelight. That was episode 6. I talked about that. And they say this as in optical, parentheses, magic lanterns. I never heard that these old limelights were called magic lanterns. But these applications are being superseded by the electric furnace and the electric light so that they can lock up production and you have to pay for every freaking everything. You don't own it, right? So 1911, the and of course they say, oh, it's so dangerous, it's explosive, right? Oh no, but we've been working with it for a long, long time. Um, some other things about hydrogen, that it is hard to compress because it's like the lightest, the least dense, like gas, I believe. But it can be slightly compressed into these type of storage tanks. And then this, I had no idea. This has got to be like some very useful uh, chemistry, I guess, because hydro- hydrogen gas heats up when it expands. And I'm like, what? I had no idea. That's like wild because in like compression, expansion, refrigeration, you have like a steam engine, a pump, air pump, but let's say you're gonna liquefy nitrogen gas into liquid nitrogen, right? So you compress it into a tank, and then when you expand it, it starts to cool, and so you keep doing that, I guess. I forget the process, but eventually it'll get so cold it'll turn back to liquid, or it'll turn into liquid. But it's just wild that hydrogen heats up, and I don't know how much, but that doesn't matter. That's not really, as far as I know, one of its most useful features, obviously. So let's go more into hydrogen, because it's really the one that's been um, phased out, uh, obfuscated, fear placed into everyone, like, oh, it's hydrogen, it's going to explode, right? And we have of course, they want hydrogen infrastructure, same thing. So you put a meter on the pipe and we can charge you all for it. I did find it interesting. I forgot to research this one, but they actually have an old hydrogen pipe system that is going how far? 150 miles. So, and they're using compressed hydrogen, 21,000 kilopascals. And this is still in operation from 1938. So I believe that's probably a remnant or something. But I don't know. I'll have to look into that, because there is an issue with hydrogen embrittlement. So, I already closed it, but I'll look at what the pipes are made of. So hydrogen can cause all kinds of issues if it's not handled correctly and next to metals and stuff, because of the reactivity, and it'll weaken and all this, embrittle the metals. Now, the this is oxy-fuel welding and cutting. So today, commonly called oxyacetylene welding. So they replaced, well, they're both useful, but I'm sure we had oxyhydrogen welding, and then also the acetylene, which is a very simple substance. It's just carbon and hydrogen. So, but it burns slightly hotter than the oxyhydrogen. Here, temperatures of that. Oh, so they even have like propane air. Okay. Oxyhydrogen burns at 2800 2800 degrees Celsius, about 5,000 degrees Fahrenheit. And then the oxyacetylene burns up to, it's like another 1,300 degrees Fahrenheit, 3,500 degrees Celsius, so extremely hot. But then, and the process doesn't look like it's really changed, like the machinery involved with welding and the actual devices doesn't look like they've changed a whole lot. Like when we're talking about pumping these gases through, um, for a powerful, like hot stream of welding fire, or whatever you call it. Oh yeah, if I don't use the right terms, I told you I'm not a welder. I mean, I don't care. So, um, the and then this just sounds cool. Atomic hydrogen welding. So this is one of the old atomic hydrogen blowpipes, and this looks like the oxyhydrogen burner that they used in the limelights, which just was oxyhydrogen, flame heating up limestone to quicklime, and then it would glow super bright. Uh, this is showing tungsten rods here because of the welding process, and this links, this gives all kinds of information, but let's see. Without the arc, right, okay, so just the normal flame can get up to 2,800 degrees Celsius, but with the arc, we can get it up to 3,400 to 4,000 degrees Celsius. Okay, and an acetylene torch merely reaches. And so the replacement for this today, I believe, is TIG welding, what people use today. But with TIG welding, you need an inert gas, like I think it's argon or helium that they use today. And it's like, where do you get that? Right, you have to go through a licensed supplier and all kinds of regulations, and I have to be licensed to work with it. I looked a little bit I was curious about welding and stuff, and it's like I'm too old to try to enroll in something. I just wanted to understand it and better. Okay, and so the reason for this is that the hottest, or the metal with the highest melting point, is tungsten. So if you want to weld tungsten, or work with that metal, cast it or whatever, I don't know, you're going to have to use oxyhydrogen or this atomic hydrogen welding torch. So this Wikipedia links to this interesting YouTube video, but let's see, where was it? Here they describe it. It's pretty cool.
The unique feature of this process is the use of a hydrogen flame to surround the arc. Hydrogen gas flows out through the nozzles of the electrode holder, around the electrodes, and the arc. The hydrogen flow cools the electrodes and prevents their rapid evaporation. The action of the arc changes the hydrogen into atomic form. Hence the name atomic hydrogen. As the atomic hydrogen contacts the work, it changes back to its molecular form. A rapid transfer of heat is obtained. The gas flame shields the molten metal and reduces most oxides that may be on the surface.
Well, that's cool. It's nice.
The weld is clean and smooth, with practically no slag or spatter.
So this is from a instructional video from 1943, because they had a device from General Electric for this as an oxyhydrogen torch, and it was used a lot of electricity, but it water, and it split the water into oxygen and hydrogen. And I just got to show this, because in episode 5 I talked about episode 5 I talked about the watchmakers, the Waltham watchmaking thing in a factory in Boston. But where was it here? Number one, I forgot about the old steam whistle. Where did that come from? A steam engine.
And speaking of precision, here's Joe McGee again.
Joe McGee in the watchmaking facility or factory. They were making pocket watches exactly like what that guy pulled out of his pocket, and then it broke. And then he's gonna use the oxyhydrogen flame to fix it up, or the oxyhydrogen welder there from General Electric. So it just was interesting where they get that from. And so the oxygen and the hydrogen gases, we get that from electrolysis, applying electricity to water. And this has been around a long time as well. Do they have the device here? Oh, I thought they had the electrolyzer here. What was the other one? Well, let me show you the electrolyzer stuff, because you just need the anode, cathode, and then it splits them out. It does. They saying DC, direct current, and it uses a lot of electricity, but it goes back to 1834 here when Michael Faraday first introduced the term. Let's see. Okay, that was Edison. Oh, here's the electrolyzer patent, or I'm sorry, yeah, from 1884. But the thing that's interesting is I found reference to this illuminating gas. So that's what it used to be called. And then another place I saw it called water gas because you're literally producing water from it, right? When it burns. And this device, well, anyway, you can see, did I highlight something? Oh, just talking about well, this was interesting though. They just describe it, but they're like, oh yeah, the gases and the gases can be used with absolute safety. Oh, if they are passed through a volatile hydrocarbon. So, oh, well, they're in this device here, this tank on the right has some sort of hydrocarbon liquid that then kind of gets carried with the hydrogen and then burned. But as far as I understand, it was, or what I think that was for, was to give the flame more color so that you could see it burning more easily. Because I think that is a issue that either the oxyhydrogen flame, yeah, maybe the oxyhydrogen is clear, colorless, and you'll see maybe steam vapor or something come up. I don't know. I've never seen one burning. Technically, I guess I could look that up. And that's talking about the steam engines. And then how much the water, if we're gonna burn hydrogen gas just with the air, how much water vapor or actual liquid, the water vapor will go up. Let's say we capture it and condense it, right? Like how much water gets produced. And this I just found, it's probably like some chemistry question that somebody was asking, but it'll give you good formulas to figure out how much you would get. But in this case, we would get about 70 grams of water when we burn about 8 grams of hydrogen gas. So no, that's not much water, but I mean, it's like if you had burners and stuff that were sealed in a way that they let the heat, they wouldn't build up pressure and let some of the pressure and heat escape, but captured the water vapor that was condensing, right? Like this, having a cooktop, and then, oh yeah, what's this? Oh, that's our distilled water from our burning of the hydrogen gas. Like, why even blow it out the smokestack? Just capture it and you'll have clean distilled water. That's too simple. It's so simple. Why aren't we doing that, right? Sorry. And okay, so let's look at some of the older tech that they used to generate the oxygen and hydrogen. Was it this one? Yeah. So this is another old magazine. I'll provide a link to this one. I think this was from 1921 or something. Gas torch and they call it THERMIT welding, thermite. And so this is down here. It's a better photo. This is one of the electrolyzers that they had, that they describe in here. And it's interesting that it looks a lot like a radiator for a car. And even this is kind of a cutout and some more schematics of that. You got the other thing that's interesting is the use of asbestos. But they had them in sacks and stuff, so the asbestos was bound up. The danger of asbestos is if it's you're breathing it in, but if it was all bound up in whatever substance, should have been much safer. And also, this whole unit's all sealed up, but it gives you and then the power requirements. But it gives you a good breakdown because we have anode and then layers, anode, cathode, and then a separator or insulator. And the water that they use in the electrolyzers, they typically it's like adding caustic soda, caustic potash, because that is adding electrolytes into the water and will help the conductivity. So it will increase the efficiency. And then the power, I had the power highlighted here somewhere. Was this it? No, I didn't highlight it. But the power requirements. So each of these cells are intended to run on a normal amperage of 600. Seems I'm not an electrician either, but I did look up that this would be 1320 watts if that's correct, because each one of these use 2.2 volts and 600 amps. So I don't know how many you could run or how that would work, but they're describing going up to 1,000 amps. In actual figures, so what is the number of cells they're using? Because we can get up to 600 cubic feet of oxygen and 1,200 cubic feet of hydrogen per 24 hours at 600 amps. Okay. So yeah, this even looks more like an old radiator. But it's nice. You can see all the different chambers, different feeds, output. And then this goes into some good detail as they're showing like stacking these and we need more production, just add more cells here, more electricity, sure, of course, but they're showing like how modular all of this was or could have been. And here they're giving a diagram of of a production room, where here on the right they have a bunch of those cells, these like these cells here, like this arrangement, but like imagine 50 of them in a row. That would be here. And then we have oxygen compressor, hydrogen compressor. And what they're showing here, I believe, are steam engines, or they could be belt-driven motors coming from a powerful enough line shaft outside somewhere to a more powerful steam engine. I don't know. But they also, what's interesting is they show large storage tanks here. As everything's doing the work, we just let the work go and pump into these large holding tanks. And so this is a layout of a 50-cell plant. And the hydrogen is, you do produce more hydrogen gas, but it's also because it's so not dense. It's so light, and it is a lot harder to compress. I'm guessing these tanks are not, well, I guess they are compressing because we got a compressor. So I don't know what pressure they could be up to. And then they even go into a much larger operation where you have like 200 cells and bigger tanks. And then they go into the cylinder storage, because we're doing welding with oxyacetylene. We need the oxygen tank, the acetylene tank. So same hydrogen, oxygen tank, hydrogen tank. And then storage for these cylinders, compressors to, whatever the best pressure for the gas and the tank. Switchboard meter. Okay. So you kind of get the idea of that. And yeah, where did all this go? This was like in 1921 or thereabouts. And so, it had to get phased out, because all you need to produce these gases, what raw material do we need to produce these gases is water. Yes, the machinery, I know, but we're starting with water. And then they go into some more nice detail on the production, oxyhydrogen production cell. They also had acetylene production as well for the oxyacetylene. And that, where was that? Oh, here's one of the tanks, or one of the production units. Acetylene generator. Okay, so you're creating acetylene, and anyway, it doesn't matter that process, but just to show you, it existed, and it's just carbon and hydrogen. So, where are we going to get the carbon? Coal. Where are we going to get the hydrogen? Water. Oh boy, that's oh. All right. What is this? I didn't look at this. Oh, this is just a Navy type acetylene plant layout. Navy type. This was something Navy didn't mean like naval. I forget what they meant by that. And then they show like the is this oxy? They don't say if this is acetylene or hydrogen and oxygen. But the welding unit and the everything looks very similar to what we have today. Okay, I think that's all I wanted to show on this. Oh no, I did want to show one other thing. But with the when you're doing this oxygen, hydrogen, or oxyacetylene welding, and let's say you want to just cut metal, like we're cutting like a 1 foot thick piece of iron or something, and the oxyacetylene, I guess, with enough of pressure, air pressure, pushing these gases out and the flame out, they can cut like metal that's like freaking 10 feet tall or something, 10 feet high. It's crazy. But you need this pressure. So it's like, where are we going to get the, like today? Okay, I got a whatever setup and I need pressure. So yeah, we need some separate device that we plug in, or it has a separate generator that either runs off diesel or natural gas or something. And then we got to run all that to build up the pressure that we can use the device with, right? I mean, if it's, something more than what's in the tank that you need to like give it some real gusto, I guess. So what I'm getting at is Oxy-fuel portable pressure generator. So I mean, if you have you had a tank of oxygen, tank of hydrogen. Oxygen's not flammable, but I think acetylene needs a much higher like heat source to ignite it, or if it's just the acetylene, I mean, and it's probably not the right application to burn oxygen and acetylene to. What I'm saying is like, why don't you just use the fuel that you're carrying to heat up a tank, like a tiny steam engine or some sort of tank system here that you can build up the air pressure that you need, right? You're carrying the fuel, everything you need in there. Or I don't see why not. Like, oh, we need more pressure. Let's use a little of our hydrogen gas or whatever to get our pressure creating device going. Okay. But let's go along these lines when we're talking about going back to like steam engines and stuff, right? Because the idea with steam engine, or the thought I have when I envision the steam engines, much of it is like from old movies and stuff about trains, where the trains are like, and it's a steam engine, and just huge amounts of billowing smoke and stuff coming out, right? Because that was what they were like, oh, what do we use to generate the heat to create the steam? Wood or charcoal, or wood or coal or coke, or and it's like, why when you have the oxygen and hydrogen gases, right? I mean, so I mean, part of it, like, what was it originally called a steam engine because the output was steam? All of the output, not all of the output was steam. uh Gases, I mean, take I'm not talking about the energy, the mechanical energy. I'm talking about like the waste that it produced was all steam, I believe, originally. Because wouldn't you? um let's see, is it this one? I gotta find it, hold on a second. No, not that one. No, it was back at this Cassier's boilers. Yeah, this the one. Yeah, this one was with. I'll provide a link to this one, but this was talking about the boilers at the World's Fair. That then the boilers to produce the steam for the steam engines at the World's Fairs, right? And well, this is a good cutaway. You can see all the different pipes and platform here where the wood or uh, coal or charcoal or coke or whatever they used was being burned. And I don't know the air requirements, right? Because if you're like, you're burning wood, you need drafting, you need airflow, you need that oxygen to get in there, so the flame, more oxygen, like a billows, right? To And that'll bump it up, burn hotter, faster, right? More heat. Um, and oh, this is an interesting one. This is, I mean, it looks like a photograph, but then it's like missing so much detail. I don't know what process they use, but these guys are actually building those this is a set of boilers. And look, I mean, they're massive. Yeah, here's a good cutaway that I want to show. This work. The okay, side elevation of root boiler exhibited at Chicago World's Ex or whatever Columbia Exposition in Chicago. So here they're showing like a bed of coals and stuff, and I guess that's the ashes down here at the bottom, right? And then okay, we're heating up all the piping, and the water's boiling in there, and they had to get it up depending on the steam engine. It had to be up to a certain psi, pounds per square inch of steam pressure, depending on the unit. I was reading different numbers, 150, 180. I don't know if it went much higher than that, psi on some of these. But, and then, right, and then it drafts out, and somewhere here is the exhaust. Somewhere here. Or here. It's just a cutaway section. But it's like, why? When you have oxygen and hydrogen to burn, and it just is going to produce more steam, and it's going to burn super hot. I mean, you could have tanks that already have like on heat if you want, but I mean, you don't need crazy amounts of heat. We only need 100 degrees Celsius to get the water boiling. I mean, a little more, right? So just having hydrogen tanks and burning it, like opening up the flue a little bit to allow air in, burn some hydrogen, and like you could keep the heat level in this way up, right? And the other thing with with hydrogen, it's I don't have it. Do I have that up? Probably closed it. Hydrogen has like the highest heat carrying capacity of any gas, meaning it itself, the hydrogen gas can get super high in temperature. There is a point where it actually spontaneously explodes, but you can bring the hydrogen gas up to like the explosive temperatures around like 570 degrees Celsius or something. So say you could bring hydrogen up to 400 degrees Celsius, and then have it circulate through heat exchangers, right? Like we're not actually burning the hydrogen gas. We're just going to heat it up and then bring it through a heat exchanger that then transfers the heat into the water so that we don't even have to burn the hydrogen. Okay? Yeah, there's this issue of the hydrogen embrittlement with metals and stuff, but I mean, they had those pipes in Germany, so there's got to be, like, it can't be that difficult to get around that issue. Okay? So the other thing when we're talking about refrigeration, right? Same thing. Like heat exchange, you need to increase the efficiency of steam engines to get into steam turbines. You're going to need a condenser. The steam passes through the steam engine cylinders and whatever, and then basically we got to condense that steam back down into water to go through the system again. So same thing, like on the if we have hydrogen heat exchanger to quickly boil some water, piping 400 degrees Celsius hydrogen gas through a heat exchanger, that water is going to boil really quick. And then, depending on the size, right? And then the opposite, we need to condense the water quickly. We can it would make sense to use the same gas, like hydrogen. We could cool it down. I mean, it's a very low temperature hydrogen is the is the the temperature at which hydrogen turns to liquid is like one of the coldest temperatures. It's like it's close to absolute zero. It doesn't matter. But so my point is, like, you could cool down the hydrogen to like minus 100 degrees Celsius, minus 200 degrees Celsius. It would still stay a gas. And so you could have your heat exchanger super cold to condense, right? And the efficiency would just go through the roof on this stuff, in my opinion. The other thing with hydrogen, right? Like when we're talking about heating it. So say you have these heat exchangers going through the for heating the water and then condensing the water, right? And you're like, oh well, we need to get our hydrogen up to 200 degrees Celsius. Say we have a tank, and that's what we're going to start feeding in for the hot side, right? To get everything going, right? And we need to produce steam, so we need to heat up the hydrogen, right? Okay, well that's where the heliostats come in. So as soon as the sun comes up, we could hit that hydrogen up to the explosive temperature really quick. But say, oh no, get the tank up to 500 or let's say the hydrogen tank that we're going to use in the heat exchanger, 200 degrees Celsius. Okay, boom, sun's up, heliostats. It's like that, 200 degrees Celsius, the tank. Now it's running through. How long is that going to run? Because you're not burning the hydrogen, you're just transferring the heat of it. And now you need more heat, heliostat. Oh, well, we have to run it at night. Okay. But the other thing is with, like, imagine you talk about remote energy, right? So say you have a steam tractor, a steam dump truck, or steam engine powered big old truck, big old tractor, whatever it is, and it's got a hydrogen tank on it, and you're like, oh, we need to get our steam engine going, and you're like, oh, what would be the remote energy? The heliostats that sent heat to your steam engine or your hydrogen tank, right? Like, well, how far could you send a beam of light to heat something up, like a laser, not like a really, like infrared or something. Oh yeah, we could like concentrate light and just shoot it at that unit and heat it up to 200 degrees Celsius, and then off it goes, because now the steam engine's got enough juice, enough power to energy. So so it's so simple. It's anyway. Okay, so hopefully you get the idea of that. It just makes so much more sense. Oh no, we have to burn wood or coal or charcoal or whatever for why? It makes no sense to do that. Like when you can create oxygen and hydrogen gases. Okay, the electrolyzer. Let's see next. Oh, and when I talk about the heliostats, I'm just showing this. The patent doesn't matter, like what it is patenting, because it's just patenting this, what they're calling it, a vapor engine, but boiler and condenser, and there's the patent number. But the reason I'm showing this is because I always find this stuff is fascinating to me, because the truth is in plain sight. Because here they're talking about this boiler condenser unit that they're patenting. They all need a heliostat and reflector to concentrate the rays of the sun on the boiler. Meaning you could just have your boiler, forget what I was talking about, like using hydrogen for the heat exchangers, right? Like you could just point that and like, oh yeah, get that water boiling there in that tank, heliostats. And you're like, I talked about that in the very first episode. They have a experimental solar furnace in France. It's a lot of heliostat mirrors, but they're able to get over 2,000 degrees Celsius. Oh, I don't know. Can we get up to 100 degrees Celsius to boil some water? Oh, we'll try, Bob. God. Okay, that was that. converting hydrogen gas when you burn it, how much water that gets. Okay. Gas torches. I don't think I want to show anything out of this one. But I will provide a link to this one. Now, there's so many things with hydrogen gas. Like one of them, let's see. Where is, I'm missing an article, aren't I? Find it. Oh, this one. Okay. So the other thing with hydrogen, obviously, right, is in the use of airships, zeppelins, blimps, right? Today, helium gas is used, as far as I know. But I do want to I'll give you a link to this article because it's just this guy is going to give you more evidence than I can. He's a chief economist, and he's saying, hey, guys, let's bring back hydrogen lifting gas. Oh, no, it's too dangerous. Like, oh, remember the Hindenburg? Yeah, he even talks about that in here, that they freaking coated like some of the Hindenburg shell with like some sort of flammable material. And they didn't, yeah, it was by design. Like, oh, the humanity, never use hydrogen again. Right. Take it away so that we can't have sustainable economy, you know? And it's funny, this guy is, where is it? I'll just give you the link to this because I didn't highlight anything, but he's part of some abundance, what the heck was it called? Abundance Initiative? I forgot where I saw that. Well, anyway, he talks a lot and will give you lots of reasons like, oh, yeah, that makes a bit of sense. And every time you're like, why aren't we doing that? I think we can answer the question, you know, it's like, that's by design. Stop listening to these clowns that say they freaking know how to, we know how to this new latest technology that we're selling you is going to solve everything. We need to go back in time, not back to the future. So it's just fascinating talking about the how this stuff got removed from our civilization, our economy, our industry, and everything, right? It's a little windy. Now, the other thing with talking about the electrolysis, right? Like in that 1920 something where they had the cells, they were using a lot of amperage and the low volts, high amps. But there's so much more with that can be done, I believe. Like, for instance, they're just in this article, they're producing hydrogen from ultrasound. And there's some fascinating chemistry or physics involved with this, but basically it's like the ultrasound like vibrates the water molecules so much it causes some captivation or cavitation or something, and it splits the hydrogen off the oxygen. Fascinating. So here, power ultrasonic at greater than 100 kilohertz, they say, will split the water into free radicals and hydrogen. Well, what's the free radicals? Is that just the oxygen? But the point I want to make is that they're talking about different frequencies, and the thing that we're also locked into with electricity, right? It's at, oh, if I get something wrong here, sorry, but 60 hertz, the electrical frequency, when the electrical plug, 60 hertz, I believe. But that's not the optimal frequency for like decomposing water into via electrolysis. You can have different frequencies of electricity, and it's like, what? Yes, why not? It is just a waveform, right? Or anyway, it doesn't matter. You can. If I say it wrong or something, doesn't matter. You can. And so there is, was it this one? Darn it. Where did I? So besides the ultrasound, there's also hydrogen plasma, where it's just you get it up to that high temperature, and then it changes basically form, I guess. And the point of this is that this article from the Journal of Sustainable Metallurgy mean, there's so many of these different journals and silos of like knowledge and information, and like no one talks to each other, it seems like, or there's no one doing, like, everyone is so specialized. And anyway, when we're talking about metals, right? As far as I know, the majority of metals, like if we're just talking about, oh, this is a block of iron ore or something, the iron is trapped in there as like iron oxide or the copper, whatever, copper oxide or aluminum oxide. There's always like a natural binding with oxygen in many of these cases, probably other things too. But it's like, okay, if you could free or what is going to bind with the oxygen is hydrogen, right? So this guy's talking about changing the way we think about purifying metals to use hydrogen gas for metal refining, oxide reduction, and let's see. Well, he also says that it's been proven in a laboratory. Reacts, okay. Scale up, okay. Is that all I had highlighted here? Yeah, they talk about using either DC or AC. In that other one, they only mentioned DC, direct current, alternating current. So here, I mean, this is really groundbreaking to me. It's like, because I mean, I don't know. I don't need to show you guys like a smelter or something, like how they melt down and purify metals in this massive smelting process that uses a lot of fuel, I believe, and carbon. I'm not sure the whole process. I'm sure it depends. You know, you're doing aluminum or iron or whatever, but they're claiming that it can reduce a lot. Hydrogen plasma can reduce a wide range of metal oxides. So I mean, that's huge. Okay, pH. Oh, and here's some of the metal oxides. Okay, iron. I don't know the rest. Chromium. I had a pause. So in this one, they kind of confirmed that the effect of the electrical variables, the electrical frequency on the production of the hydrogen oxygen, because in here they're describing the different waveforms and that the DC input was better than AC on the production, but also that they're experimenting with different frequencies in here somewhere, I believe. The other thing that I want to mention, because in the patent, like they call it here illuminating gas, and one of the things I'm pretty sure that happened is they changed the terms, because like today we say like, oh, I gotta go pump some gas or I gotta get gas, right? And here, this is again in the Cassier's magazine, the engine, like many of those already described, is adapted to use gasoline as well as gas. And so they reference like, oh, coal gas or this or that, but it makes sense it would be hydrogen gas. They describe a lot of like stationary gas engines that they call them in this magazine, you know, and they all have like a wheel that then turns some other sort of belt driven type of device. But on all of these, or so many of these, were originally designed to run on hydrogen gas, I believe, because they would, instead of like exploding a, you know, carbureting air and gasoline spray into the cylinder and then exploding that with a spark plug, you just maybe do the same with hydrogen gas, and maybe some other sort of, maybe the hydrocarbons really help prevent like that hydrogen embrittlement type of process. I don't know. Or maybe it's to like provide more to the flame, just so, or I don't know. But just using hydrogen gas would make so much sense inside of an internal combustion type of engine. And so they have a lot of these described in this magazine, these different types of stationary engines, right? Like, and with the wheels here were for belts to then drive, other equipment. And this makes sense in like a factory type of situation where you have your main steam engine, or you have whatever type of setup somewhere nearby where you're producing the hydrogen and oxygen gases. But it doesn't make any sense to pipe it somewhere, like to run these machines, when you just have like some sort of simple tank that you bring in, or well, I guess you could pipe it, because they had that underground pipe and hydrogen gas pipe in Germany somewhere, transporting pressurized hydrogen gas. So, going back to the hydrogen plasma here, and the what you can do with like the purification of metals and stuff like that. Uh, okay, we talked about, the ultrasound. So I think yeah, there is probably a sweet spot with like ultrasound, electrical frequency, and everything that can get the hydrogen production up, probably to levels that make it a little more feasible. And this one was interesting. They have this is reducing hydrogen. I'm sorry, iron ore into hydrogen. Gosh, sorry, iron ore in hydrogen to purify it, reducing it into pure iron. Oh yeah, same one here. That's the same thing. And then more articles along the same vein saying that, this hydrogen plasma, we can use that to purify all kinds of metals. Okay. A metal stable phase shocked bulk single crystal copper. Why did I put this in here? I think because I was thinking, like, if say you had a sealed chamber, right, or something, and you needed extreme an extreme amount of force to, like, this is talking about shocking these crystals with immense force or something, right? Hydrogen would fill that need as well. Uh, you could have it sealed and not even have an igniter. Uh, oh gosh, I gotta find that. It doesn't matter, but you can look this up. This is unbelievable to me. You could theoretically, like, the chamber would probably explode, but you could theoretically have a sealed chamber, let's say with some sort of like piston action or something to release some of the pressure. Um, and that, oh wait, though, hydrogen gas heats up as it expands. Oh, so would it all explode? Like if you had a sealed chamber and hydrogen gas in there, and he heated the whole thing up to like that 570 degrees Celsius, the hydrogen would spontaneously like explode, combust with immense force. So if you could like direct that force out, and then like as soon as the hydrogen cools down just a few degrees below that temperature, it'll stop the process, right? It's just fascinating to me. And you're like, oh no, that everything would explode. I mean, but theoretically, if you had something small enough, a small amount of hydrogen, and had it, I don't know, it just seemed fascinating to me. It seemed like that would be like some super advanced tech that I could imagine, but what you could do with that, because it would just be all sealed, and you could forever convert heat into mechanical energy, like forever. Like it wouldn't, if the if this chamber or whatever device was 100% sealed, it would last forever. I mean, as long as the material didn't like break apart or explode, or that embrittlement and stuff. Yeah, but there's the explosive nature of hydrogen itself. That's why the Hindenburg and can't use it, right? Uh, or it's so dangerous. You're gonna blow up the house, or you're gonna blow everything up, and it's like, no. I mean, the fact that they had this stuff, you know, 200 years ago or whenever, and Well, we're too stupid to use it today? No, of course not. It's just say like, oh no, you guys can't use that. That means you won't have to come to us for every little. You won't have to come to us so that we can't nickel and dime you to death like everything is today. Okay, the other thing I wanted to show, which I don't have it up, of course, is I can't find that article now I had, but just like they were using hydrogen in these reductions for iron ore, I found some theoretical thing where they were talking about actually converting rust, which is iron oxide, back into iron by using hydrogen. Because anyway, and so if you have like steam engines and stuff, we're talking about turning the wheel, so grinding down, powdering into turning ores into fine powders, so that the hydrogen can get in, would probably greatly increase the efficiency of that stuff too. I'm sure that, in these descriptions when they're talking about, one of these had the chambers in it. They're trying to create like laboratory type of chambers, small ones that they can experiment with this stuff with. The other thing I wanted to bring up is there is this form of hydrogen, or it's actually arsenic and hydrogen combined, arsenerated hydrogen. But this, the reason I'm showing this page is the word origin. This goes all the way back to 1805, okay, where this term came up. And today it's called, we're calling it arsine. It's poisonous, yes, and I'm not saying that we should be using this, or I am 99% sure that the ancients were using this. Number one, we have a reference to that term way back in 1805. Okay, so it had to be known in some way, shape, or form. But this is fascinating. That this substance, this arsine, is used for chemical vapor deposition. And this chemical vapor deposition is used to produce high quality, high performance solid materials. Quality, engineering candy. It's like, the quality of this material, and performance. That's what engineers want. And so you're like, wait, yeah, I think they probably were using it, or they had it available. They were so much more advanced. And to show you how my mind works, like why I think that, it's kind of okay. This is a huge stretch, but there was in Popeye, the old cartoon where he like squeezes a can of spinach and he gets super strong, right? There was either an episode or a couple episodes where he goes back to ancient Rome. And I remember watching this as a kid. I can't, it doesn't matter to show you the cartoon, but when he's back in Rome, he doesn't have there's no cans. He doesn't have a can of spinach to eat. So he smells garlic. And when I watched this as a kid, it made zero sense. I'm like, why isn't he? Because it made sense, like spinach. Oh, you're getting all this nutrients in your body, right? And it's like I'm not going to get that if I just smell spinach ever. And the same with the garlic. I'm like, why didn't he just eat the garlic? When I was a kid, eating a clove of garlic was probably as bad or equal to eating a can of spinach in my mind, because the canned spinach is disgusting. But I think this is like some Duper's Delight thing, like they're pointing to it because, I didn't show that, but like, why didn't he eat the clove of garlic or eat the bulb of garlic? That would make more sense, right? Like you're getting the nutrients in your system, not just by smelling. But that's why I wanted to say that, is that this arsenated hydrogen has a garlic-like smell, a scent. So if you are a builder, this would give you power. Using it in the chemical vapor process. Yeah, chemical vapor deposition. I have no idea what this is. Like, again, all of this stuff is siloed and stuff. I mean, couldn't even get in to look at one of these machines. I don't have the right licensing or certifications or whatever. Like, oh, don't touch that. Okay. Oh, okay. So I just thought it was. I just when I read that about the arsenated hydrogen, that it smells like garlic. I was like, that this popped into my head immediately, and I don't know why, but I think it's well because when I was a kid, it stuck in my head. Like, it didn't make sense to me. Like, like why didn't you eat it? Like, just smelling it, like it doesn't enter your body the same way. It doesn't go through the stomach, right? So anyway, okay. Let's see. I think that was about all I wanted to talk about today. Yeah, let's call it. And well, the next time I'll go into building materials, I guess, because the other thing was with like the steam engines, right? Like burning coal, burning wood to heat them up to produce the steam and the pressure. Coal. Uh, well, we had in episode 6 the carbon arc lamps, carbon arc welding, which are just from simple compressed carbon rods. And then the other reason I want to go into building materials like quicklime, for example, is what I talked about with the heliostats, right? It's so much energy to cook limestone into calcium oxide into quicklime. Well, no, if you have a heliostat array that can get you up to 2,000 degrees Celsius, it's not too hard at all, actually. Oh no, we need to produce just so much, every day, all 24/7. This plant has to run producing quicklime. Why? Right? If it's for you, for your community. But going back to building, to do large pours of large pours of cement, you need fly ash because just the quicklime is a hydro or exothermic. It produces heat when it binds, when it starts the chemical reaction with water, because it is hydraulic. It will set underwater as far as whatever the right mix is, because it binds in the presence of water. That kicks off that reaction, but it also produces a lot of heat. So you can definitely create building materials just with that, like blocks of that then are stacked. But if you want to create some very large, like 1,000-ton type of block of concrete, you're going to have to use, as far as I know, fly ash, so that you don't. The binding does happen, or the process, but there's not huge amounts of heat created like with the quicklime. Anyway, so I want to talk about that next time, I guess. Okay, so that's all for now. Anyway, take care. I'll talk to y'all later. Have a good one.